I'm Gary Prizo. In this video, I'm going to talk about my experiment, the first non-zero measurement of a subatomic electric dipole moment. I'll discuss the theoretical and experimental concepts. I'll talk about a small portion of the over 1,000 hours of data I collected to make this measurement, and I'll do so in a manner that is as non-technical as feasible. If you want to see any details, please look at my paper. There's a link to it on the LOISAT website. Also, consider making a donation to the LOISAT Shields and Spear fundraising campaign, as well as to the LOISAT Detecting the Dark Matter Axion Wind fundraising campaign. First question, why measure subatomic electric dipole moments? The motivation lies in the fact that it greatly helps answer quite deep questions. For example, why did the universe make more matter than antimatter at the very beginning? If the universe had made precisely the same amount of matter as antimatter, the Milky Way wouldn't exist and our solar system wouldn't exist. In other words, that question goes to the heart of why we're here at all. One thing we do know is that for an excess of matter to have been generated, it requires our universe to violate a principle called time invariance. Time invariance refers to the notion that our universe looks the same regardless of the direction of time. In fact, it has long been known that that's not true. Our universe doesn't look the same regardless of the direction of time, and therefore our universe violates time invariance. To give an example of this, consider the possibility of a system that has a certain energy when the time is moving forward. If you reverse the direction of time, in our universe, that system may not have the same energy than when time was moving forward. In other words, the energy of the system depends on the direction of the arrow of time. Therefore, our universe violates time invariance. The violation of time invariance is integrated in the standard model of particle physics. That model explains extremely well nearly everything about subatomic particles, including the violation of time invariance. The issue is that the amount of violation is not sufficient to explain the totality of the excess of matter over antimatter at the beginning of the universe. As a result, physicists have come up with theories that go beyond the standard model of particle physics to explain the excess of matter. Often, these theories will produce larger numbers or larger values for the electric dipole moment of subatomic particles. Because subatomic electric dipole moments also violate time invariance, they contribute to the fact that the universe doesn't look the same depending on the direction of the arrow of time. It's an important measurement to make because the standard model of particle physics predicts a smaller value of subatomic electric dipole moments than the theories that go beyond the standard model. Therefore, by making a measurement of the electric dipole moments of, if possible, all subatomic particles, we'll be able to select the theories that are actually consistent with all the data and effectively reject the theories that are not. Next question is, what are dipole moments? Well, to answer that question, we're going to discuss a magnetic field that is produced by a current loop and an electric field that is produced by a battery. And we'll talk about long range and short range fields. If you look at the long range fields of the current loop that carries a current I and a surface area A, and you compare it to the long range field of the battery that has an excess of positive charges at the top of the battery and an excess of negative charges at the bottom of the battery. The distance between the excess charges is little d. If you compare the long range fields of these two systems, they are identical. They both produce classical dipole fields. And long range here really means that you're so far away from these two systems that you cannot make out the current loop at the center of the magnetic field. In other words, it just looks like a point. Nor can you make out the battery at the center of the electric field. Likewise, it looks like a point. So these are the long-range fields. What we're seeing in this picture are actually the short-range fields. We clearly see the current loop and we clearly see the battery. And the short-range fields look completely different. If you consider the short-range field of the current loop, the field lines all broadly have an upward direction, and there's no abrupt change in direction of the field lines. Contrast this with the electric field lines of the battery, the short range field. Above and below, you have this upward trend, but inside the battery actually goes from top to bottom. We can say that the electric field is negative inside the battery as compared to the electric field on the outside. And so we'll use that language that the electric field, the internal electric field of a battery is negative. And so when you move from the bottom or below the battery and you enter the battery, there's an abrupt change in the direction of the electric field line. And this difference between the short range fields of a magnetic field produced by a current loop and an electric field produced by a battery is critical in understanding how electric and magnetic fields behave in matter. This is something that's important to understand because my experiment relies on electric and magnetic fields in matter. Having compared the basic difference between the fields produced by a current loop and by a battery, let's actually define dipole moments. Here on the left, I have a green arrow that represents the magnetic moment of the current loop. It's a vector and it has both a direction and a magnitude. The direction is given by the direction that is perpendicular to the surface area of the current loop, and the magnitude of the magnetic moment is equal to the current carried by the current loop multiplied by the area of the current loop. Likewise, the electric moment of a battery is a vector. The direction is given by the line that connects the negative charges, the excess negative charges to the excess positive charges. And the magnitude is simply equal to the excess charge Q times the distance between the excess charges, little d. In fact, what we'll generally say is that the dipole field is generated by the dipole moment. So the dipole magnetic field is generated by the magnetic dipole moment, and the dipole electric field is generated by the electric dipole moment. So let's talk about the energy that dipole moment has when it is immersed in an external field. On the left, we have our magnetic moment, and it is immersed in what is a uniform magnetic field. It doesn't have to be uniform, but there's no reason to add additional complexity. So uniform, of course, just means that the magnetic field has the same direction and magnitude everywhere in space. The minimal energy configuration of the magnetic moment in this external magnetic field is perfect alignment with the magnetic field lines. So if the magnetic moment is in its minimal energy configuration, in other words, it's perfectly aligned with the external magnetic field lines, to rotate it away from that minimal energy configuration, you have to produce energy. You have to provide it with energy. You have to provide work. And the amount of work that you have to do to rotate a magnetic moment away from its minimal energy configuration is just proportional to the magnetic moment. Likewise, on the right, we have electric moment that is immersed in a uniform electric field. its minimal energy configuration is when it's perfectly aligned with the external electric field lines. So if you want to rotate an electric moment away from its minimal energy configuration, you have to do work, you have to provide energy, and the amount of energy you have to provide is just proportional to the electric dipole moment. Now, as I said, electric and magnetic field lines in matter is a key aspect of my experiment, so let's talk about this in a little more detail. So here I drew a magnet. The way I know it's a magnet is because all of the bound currents are actually aligned. They don't have to all be aligned in a real magnet, but a substantial fraction has to. Here, the word bound just refers to the fact that these are not simply classical current loops. They are magnetic moments that are associated with each site in a lattice site that makes up the bulk matter. In solid state physics, bulk matter is often described as a lattice where each site contains a molecule or an atom. And that molecule or atom is bound to the lattice site. Any property that that molecule or atom has will therefore be bound to that lattice site, including a magnetic moment. And so all of the magnetic moments are aligned here, and they produce a magnetic field, a macroscopic magnetic field, that can actually be described by one large bound current that goes, that runs around the surface of this magnet. And so, in fact, if one wants to visualize a magnetic dipole field, one can always put a bar magnet in iron powder and see all of the iron particles align along the field lines. It makes a very nice dipole field configuration. But here you have this large bound current that can properly describe the field of this magnet, equivalent effectively to just adding up the magnetic field's point to tail of all of these little bound dipole moments. So what that means is that if you have a torus, and it can be magnetized, and you magnetize the bound dipole moments, the bound magnetic moments, such that each one is perfectly aligned or parallel to the circular axis of this torus, on average, you will produce these circular magnetic field lines. And this can also be imagined exactly like we talked about this large bound current on the surface. Effectively, wound around this torus would be a solenoid around its entire circumference, which would produce a solenoid field and these circular field lines. So of course, here there's no north and south pole. Here this magnet would have had a north and south pole to actually attract the iron particles. But if for such a magnetized torus, there's no interaction really with iron particles because there's no south or north pole. There's no surface. And so that doesn't mean that we can't actually experimentally verify that these circular magnetic fields exist. One can do this using, for example, the Aharonov-Bohm effect. So these are magnetic fields in matter. Now let's see if we can do a similar analysis with electric fields in matter. Here you have an electrically polarized bulk matter. At every lattice site, you have a electric dipole moment with an excess of negative charges at the bottom, say, and an excess of positive charges at the top. And so here it's polarized because they're all pointing in the same direction. So perhaps the bulk matter will also have these average electric field lines, just like we saw for the magnet. Actually, the answer is not that simple because you can create alternative electric dipole moments that have opposite polarity with the bound dipole moments. So here you have a bound electric dipole moment, but you can also create with opposite polarity an electric dipole moment where you have an excess of negative charge at the top and an excess of positive charges at the bottom. And so as you move through the bulk matter that is polarized, in fact, the average electric field is zero because it constantly changes sign. Here it goes from top to bottom, and inside here it goes from bottom to top, and inside one of the bound charges, it goes from top to bottom. So the average electric field will be zero, except at the surfaces. So for example, on the top surface, there's an excess of positive charges because nothing cancels it. And likewise, at the bottom, there's an excess of negative charges. So you do have an electric field, but it is entirely produced by the excess charges at the top surface with the bottom surface. The internal polarization contributes nothing to the electric field. So if we want to try and produce circular electric field lines in the torus, we fail because there's no surface and therefore there's no excess surface charges. Everything cancels in pair. The average electric field, constantly changes direction, so the average electric field is precisely zero. That doesn't mean that it is impossible to have circular electric fields. So here you have a configuration where in fact they do exist. You have these circular electric fields, but they're not due to polarized bound charges. They are the circular electric field lines are produced by or induced by a linearly increasing magnetic field that goes through the center of the torus. Linearly increasing in this case means that that if you wait twice as long, the magnetic field going through the torus will be twice as large. This will produce circular electric field lines that are constant in magnitude. And so if you have a constant electric field that has circular field lines, that means that you can have a current. Now imagine that the bulk matter was a perfect conductor, that it has no resistivity. That would imply that the current would linearly increase. Again, that just means that you wait twice as long and the current going around the torus or this loop is twice as large. So one may wonder, since magnetic fields can do no work, where exactly is the energy for this increasing current coming from? It comes from the generator that is actually powering this linearly increasing magnetic field. That's the ultimate origin of the energy that is driving this increasing current, and this is how energy is conserved. Having discussed classical electric fields and classical dipole and dipole moments, let's see how these translate in elementary particles. In this talk, what I mean by an elementary particle is any particle that follows the laws of quantum mechanics and that are point-like as seen with from the perspective of a non-relativistic particle. And non-relativistic, of course, means that the velocities of all the particles in our system, in our conductors, are well below the speed of light. And nowhere close that one could actually see, for example, the internal structure of protons and neutrons or the internal structure of nuclei. So in this talk, we'll just talk of nuclei, protons, and neutrons as elementary particles that have no structure, that follow the laws of quantum mechanics exactly the same way electrons do. And when we talk about, when I illustrate a magnetic moment here and an electric moment here, these are two properties of the same particle. They're just illustrated in two different drawings simply to clarify how they change or how they behave, just generally speaking, and it'll be a little bit clearer. And so magnetic moments in elementary particles have long been measured very accurately. So the question for physicists was, do they have electric dipole moments? And so the first attempt to actually measure subatomic electric dipole moment was in 1951 by Smith, Purcell, and Ramsey, when they attempted to measure the electric dipole moment of the neutron. Despite the fact that their experiment had excellent sensitivity, they weren't able to measure anything. And so that implied that the electric dipole moment of the neutron must be nearly zero. And also, there's a parameter in the standard model of particle physics that contributes to the electric dipole moment of the neutron. And that parameter had to be nearly zero. And since then, every attempt at measuring the neutron electric dipole moment has failed. And now the upper limit on the electric dipole moment of the neutron is infinitesimal. And so now the question is why? Why is it that this electric dipole moment, in fact, the electric dipole moment of all subatomic particles is so small? And relatedly, why is this parameter in the standard model of particle physics nearly zero? Well, an answer was provided in 1977 by physicists Roberto Peccei and Helen Quinn, who proposed an elegant theory that explained why the electric dipole moment of the neutron was so suppressed. And also, it implied the existence of a particle that would barely interact with ordinary matter, the matter that everything we're familiar with is made of. And on top of that, would have been produced in huge amounts at the beginning of the universe. By then, the existence of dark matter had been established. And in fact, since then, the existence of dark matter has been confirmed from so many experimental directions that it is really not in question anymore. And when the theory of Peccei and Quinn was seen to imply the existence of this particle, it immediately became a popular candidate for dark matter, because dark matter also barely interacts with regular matter and would have been produced at the beginning of the universe. That particle is called the axion. Although the theory of Peccei and Quinn has been substantially modified since it was first proposed, the search for the axion is still a very active area of physics research. And so we already discussed how violation of time invariance is a necessary criterion for the production of excess matter over antimatter at the beginning of the universe. So let's talk about how dipole moments of elementary particles change when you change the direction of time. So again, these are two properties that are part of the same particle. And so they follow the laws of quantum mechanics, and as a result, they have to follow a theorem called the Wigner-Écart theorem. The Wigner-Écart theorem says that any vector property of a particle must be proportional to the angular momentum. And so we already established that dipole moments are vectors, and therefore they must be proportional to the angular momentum. So briefly, what is an angular momentum? If you think of a spinning top on a table that spins on a single point, and therefore has no linear momentum, it still has momentum because it revolves around an axis. And angular momentum is a vector that describes this rotating motion because it has both a direction and a magnitude. The direction is provided by the axis about which the spinning top revolves, and the magnitude is proportional to the angular velocity, the rotational speed of the top. So it's a vector, and because it's a vector that comes from motion, when you reverse the direction of time, the direction of rotation of the spinning top must reverse as well. And that implies that angular momentum flips its direction. And by the Wigner-Écart theorem, that means that the dipole moments that are both vectors, so both the electric and magnetic moments, will also change direction when you reverse the arrow of time. And so that's how they transform under time reversal. But the Wigner-Eckhart theorem implies another important property that is used in my experiment. Since the magnetic dipole moment is must be proportional to the angular momentum, and the electric dipole moment must also be proportional to the angular momentum, that means that the electric dipole moment must be proportional to the magnetic dipole moment. And this is represented by this equation here, where you have the electric dipole moment, represented here by D. It must be equal to the magnetic dipole moment, here represented by M, up to a proportionality constant, little a. So that equation is extremely important for my experiment because it implies that if you align the bound magnetic moments in bulk material using an external magnetic field, and we know that the magnetic moments will align with an external magnetic field because we know that the minimal energy configuration of a magnetic moment in an external magnetic field is alignment with the magnetic field lines. And systems always attempt to minimize their energy. And therefore, if you align the magnetic moments of the bound magnetic moments, you will automatically align the electric dipole moments without, for example, having to apply an external electric field. And so this is important because it's nearly impossible really to align a subatomic electric dipole moment with an electric field because electric dipole moments of subatomic particles are infinitesimal. And so the electric field, the external electric field, would have to be nearly infinite. So it's a lot easier to just apply a magnetic field, an external magnetic field that's not even particularly large, and then align a substantial fraction of magnetic dipole moments, and immediately you will get for free the same fraction of electric dipole moments that are aligned. What about external fields? How do they transform under time reversal? So again, the same pictures as from the beginning of this video. For a external magnetic field produced by a macroscopic current loop, well, the current loop comes from the motion of charges around the current loop. So if you reverse the direction of time, the charged particles, the electrons really will change direction, and therefore the current will become negative relative to what it was when time was moving forward. That means that the external magnetic field lines will all flip. Well, what about an electric field, an external electric field? Well, in a macroscopic battery or macroscopic charge distribution, you can think of all of the charges as being static. So nothing's moving. And therefore, if nothing is moving, you reverse the direction of time and nothing happens to the electric field. The field lines are exactly the same as when time was moving forward. Now, let's immerse our elementary particle in external fields. And again, here the external electric and magnetic fields are superimposed because it's immersing a single particle that has two properties, a magnetic moment and an electric moment, here separated for clarity. So imagine that when time's moving forward, the magnetic moment has this configuration, energy configuration, in the external magnetic fields. In other words, this is its minimal energy configuration. You flip the direction of time, and both the magnetic dipole moment of the elementary particle and the external magnetic field change direction. And again, remain in the minimal energy configuration because the magnetic dipole moment is still perfectly aligned with the external magnetic field lines. So nothing has changed. The energy hasn't changed between the two time directions. What about an electric dipole moment? Here again, time's moving forward and the electric dipole moment is drawn as being in its minimal energy configuration with respect to the external electric field, perfectly aligned. You change the direction of the arrow of time, and again, the electric dipole moment has to flip, but the external electric field doesn't. So reversing the direction of time produces an energy configuration that is maximal for the electric dipole moment because the electric dipole moment is perfectly anti-aligned with the electric field. So the energy of the electric dipole moment has changed when you change the direction of time. So the particle itself, the energy of that particle has changed with time reversal. And therefore, time invariance is violated, and it is entirely due to the fact that the electric dipole moment of the particle is non-zero. If it had been perfectly zero, there would be no change in the energy of that particle. And of course, we already know that excess matter in the universe requires the existence, the fact that our universe violates time invariance, and this is just represented here. When the universe was very hot and particles and antiparticles would annihilate, the universe could produce more particles and antiparticles. In these drawings, I draw the antiparticles as electric dipole moment with the arrow pointing down. And that's just because antiparticles can be thought of as particles that are moving backwards in time in quantum field theory. But as the universe expanded, it cooled, and it didn't have sufficient energy eventually to keep producing matter and antimatter. So the antimatter just kept annihilating against the matter, and eventually there was no antimatter left. But because the universe violates time invariance, there was still a little bit of matter left, and that's the stuff that we're all made of. In practice, what we know is that about 1 part in a billion, in terms of the number of particles that existed at the beginning of the universe, actually remained after this process finished. So we're talking about point particles, and we have already discussed at the very beginning of this video that the long-range fields of electric dipoles and moments and magnetic dipole moments are identical. And because the particles are point-like, one can think that effectively we don't have to worry about the short-range electric field. After all, the particles are point-like. And so in that case, perhaps we can have a circular electric field line that can exist in bulk matter exactly the same way that it exists for magnetic fields, which we've already established is the case. In fact, the answer remains no. It is not possible to have a total electric field that has circular field line in a torus or in a circular loop purely due to the polarization of electric dipole moments. And to understand why, let's talk a little bit more about what it actually means to have a point-like electric dipole moment. It's a strange concept, and it appears to be a contradiction in terms, because we know that electric dipole moments are equal to the excess charge times the distance between the excess charges given by little d. So if you shrink a battery to a point, you're effectively bringing little d to zero, and therefore you end up with an electric dipole moment that is precisely zero. But that's not the way that you actually produce a point-like electric dipole moment. What ideally you would want is to preserve the long-range dipole field, which is outside the battery, and the only way to do this is to keep the electric dipole moment constant as you shrink the battery to a point. And what that implies is that as d goes to zero, you have to take the excess charge to infinity. And this is a process that can be done mathematically in a consistent way. And so as you shrink the particle, as you shrink the battery to a point, d goes to zero, q goes to infinity, and little de stays constant. But something interesting happens to the internal electric field lines, the short-range electric field lines. As you shrink the battery to a point and q increases, the short-range electric field clearly increases as well. It becomes extremely strong. nothing really happens to the long-range electric field because the electric dipole moment is a constant. But the internal electric field, short-range electric field, goes to infinity. And in fact, what happens is that at the single point where the point-like electric dipole moment exists, you have you end up with a negative electric field that has an infinite magnitude. Everywhere outside of that point is considered a part of the long-range field. But at that one point, you have that negative electric dipole field that has an infinite. You have this infinite electric negative field, and so when you perform an average to calculate the total mean electric field in a torus due to those polarized electric dipole moments, the average electric field is precisely zero. So still no circular current loops, even though here I have a drawing of the long-range dipole field. It could have been electric field. It could have been either for an electric or magnetic dipole field, due to a point-like dipole moment. It doesn't matter. It's exactly the same long-range field. And so it's interesting. It remains an interesting thing that the average electric field is zero, because the only way really for an electron to interact with the negative infinite electric field is if it sits somehow right on top of it. That's why I drew this little chair that's too big for a point-like electric dipole moment. But it exists, and you have to include it in your average electric field, and you get zero. So we've talked about electric and magnetic fields in matter. Well, how about matter that is in a superconducting state? Superconductors are fascinating things. The metal can become superconducting if you lower the temperature of that metal or compound below its transition temperature. For most elements, the transition temperature is below 10 Kelvin. And so superconductors, of course, imply, the name itself suggests correctly that the charge carriers feel no resistance in a superconductor. So you can have a persistent current that lasts for nearly, from the point of view of a human life, forever. And so it effectively it never really changes. And when it changes, it can be due to various reasons. But so you can have these persistent currents that can be thought of as constant and lasting forever. And superconductors have an additional property, which is that they expel magnetic field from their bulk. Magnetic fields can only exist on the surface of a superconductor up to a depth called the penetration depth. This is where you'll find the currents and magnetic field. The thickness of the penetration depth of a typical superconductor is of the order of 1/10,000th that of a human hair. So going back to the fact that in a superconductor, electrons in the form of Cooper pairs cannot feel any resistivity, it implies that electrons cannot scatter off the atoms or molecules at the lattice sites, because scattering actually contributes to resistivity. So that implies that the probability of an electron scattering off a lattice site is zero in a superconductor. In other words, the wave function of the electrons must be zero at each lattice site of the bulk material. But we know that the negative infinite electric field of a point-like electric dipole moment is located precisely at the lattice site. But from an electron in a superconductor, and again, the electron is actually part of a Cooper pair, they cannot really perceive anything at the lattice side, it's like there's a black box that prevents the electron from interacting anywhere inside that lattice side, inside that black box. And so from the perspective of the electrons in a superconductor, the only thing that they can perceive, the only fields they can perceive, electric field, is the long-range electric field. Here, the long-range electric field is denoted as E subscript lambda. Lambda is for long range. And to distinguish the long-range electric field from the total electric field in the superconductor that remains precisely zero, I call the long-range electric field the electrization field. And so with circular electric field lines in a superconductor that, for example, would have been generated through the magnetization of the magnetic moments in the bulk material that automatically align the electric field, you have these circular electric field lines or electrization field lines that can accelerate the Cooper pairs or the electrons. So this is represented here. So again, imagine that the way we actually polarize the point-like electric dipole moment is through nuclear magnetization. And so here I'm going to exclusively talk about nuclear magnetization. So you have a current loop that is immersed in an external magnetic field that will be, in my experiment, was generated by a solenoid. It induces nuclear magnetization. Magnetization just refers to the fact that there's a certain fraction of nuclear magnetic moments that are aligned with the external magnetic field per unit volume. And so that's the nuclear magnetization. And we know already from the Wigner-Eckart theorem that precisely the same fraction of nuclear electric dipole moment per unit volume will also be aligned with the external magnetic field. So since now the Cooper pairs or electrons can be accelerated by the long-range electric field, and we're polarizing them using a magnetization, the electromotive force that is accelerating the the electrons must be proportional to the nuclear magnetization. Needless to say, it also must be proportional to the electric dipole moment of the nuclei. So this is effectively up to certain factors. This is the electromotive force. And because now we're talking about a circuit equation and there's no resistivity, there is still an impedance. The impedance is due to the fact that not all the energy can go into accelerating electrons in a superconductor. Some of the energy has to go to generating the magnetic field. And this is represented by this self-inductance term. The important aspect of this self-inductance term is that it is proportional to the rate of change of the current, of the supercurrent. And so the rate of change of the supercurrent is proportional to the nuclear magnetization and to the electric dipole moment. For our experimental parameters, the nuclear magnetization follows Curie's law. In other words, it is proportional, it is inversely proportional to the temperature, and it is proportional to the external magnetic field. Since our magnetic field is generated by a current in a solenoid, the magnetic field, that means that the nuclear magnetization will be just proportional to the current of the solenoid. So one can summarize these aspects in the following way. The electromotive force will be strongest at low temperatures and at large solenoid current. So again, one may wonder, where exactly does the energy for this linearly increasing current come from? Well, actually, it ultimately comes from the solenoid current itself. Having discussed now the theoretical concepts, we are ready to go through the experimental design. And so the basic purpose, of course, to identify a nuclear electric dipole moment is to search for an electromotive force that follows Curie's law. And of course, the electromotive force being proportional to the rate of change of the current will actually be, to determine the electromotive force and its whether or not it follows Curie's law, we'll actually just be looking at the rate of change of the current in our superconducting loop. For my experiment, I chose tantalum for a number of reasons, but in large part because nearly 100% of the naturally occurring isotopes of tantalum is one isotope that has a reasonably large nuclear magnetic moment. For such an experiment, it was important to include a control element, and that control element is lead. Lead was chosen because its electromotive force is greatly suppressed compared to that of tantalum. It's about 20 times smaller in lead than tantalum. And the reason is simple. Only a quarter of naturally occurring isotopes of lead actually have a magnetic moment, and that magnetic moment is considerably smaller than the magnetic moment of tantalum, nuclear magnetic moment of tantalum. So now we have an element that is that can be superconducting, where the electromotive force is quite suppressed. And so again, the external magnetic field that polarizes both electric and magnetic dipole moments comes from a solenoid. And that solenoid is part of a larger superconducting circuit that includes a booster solenoid. The purpose of the booster solenoid is actually to induce a solenoid current, as we'll see on the next slide. And these solenoids were used for both lead and tantalum for consistency. Clearly, we have to work at sub-Kelvin temperatures and collect data at a number of fixed temperatures and a number of fixed solenoid current to verify whether or not our rate of change of current, i.e. our electromotive force, follows Curie's law. Now let's discuss the sample assembly and experimental procedure. Here's an illustration of the sample assembly, and we're going to see actual pics of the experimental components. This here is the superconducting sample wire loop made out of either lead or tantalum. The current carried by the sample loop, sample wire, is I subscript S, S for sample. The sample solenoid provides the external magnetic field in a portion of the sample wire. And as I said on the previous slide, it is part of a single superconducting loop that includes a booster solenoid. The booster solenoid is located inside this larger solenoid called the main solenoid. So there are three solenoids: the sample solenoid, the booster solenoid inside the main solenoid. The booster solenoid is wound around an aluminum core, and the leads of that superconducting circuit that includes the booster solenoid and the sample solenoid are joined in a superconducting joint represented by that copper-colored rectangle. The main solenoid leads go to the exterior of the adiabatic demagnetization refrigeration system I used to lower the temperature of my sample assembly to sub-Kelvin temperatures. Going forward, I will refer to the adiabatic demagnetization refrigeration system simply as an ADR. And so the leads go to the exterior of the ADR to a current source. So the experimental procedure is as follows. Above the temperature of the superconducting wires that make up all three solenoids. So the superconducting wires are made up of a single filament, a niobium titanium wire, and they transition from normal to superconducting at a temperature of about 9.2 Kelvin. So above 9.2 Kelvin, you apply a current I subscript A, so applied current of the main solenoid, that now flows through the main solenoid. And that main solenoid then has a magnetic flux inside it, and part of that magnetic flux goes through the booster solenoid. And so the ADR continues to lower the temperature of the sample assembly. At some point, that temperature will be below 9.2 Kelvin. And the booster solenoid and sample solenoid will be superconducting. At that moment, when the solenoids are superconducting, you turn off the applied current. And so the main solenoid is no longer producing a magnetic flux that goes through the booster solenoid. But because nature abhors changes in magnetic fluxes, immediately the booster solenoid and the sample solenoid will have a current induced in them that precisely reproduces the magnetic flux that had been previously generated by the main solenoid. So now we have an induced current that flows through the sample solenoid, and it's just labeled I subscript SOL for solenoid. Now the ADR continues to lower the temperature of the sample assembly, and at some point it will get below 1.2 Kelvin because it's bringing everything to sub-Kelvin temperatures. 1.2 Kelvin is the transition temperature of aluminum to the superconducting state under typical conditions. And so at some point, the aluminum will expel all the magnetic fields, as we discussed when we introduced some properties of superconductors. And again, now we have the aluminum blocking the magnetic flux. And immediately the booster solenoid and the sample solenoid will boost the current that flows through them in order to reproduce, again, precisely the same magnetic flux that was initially flowing due to the main solenoid. And it was experimentally and numerically determined that the boost of the solenoid current is a factor of 10. So now the current that flows through the sample solenoid is 10 times larger, hence the name of this solenoid as the booster solenoid. And so then the ADR continues to lower temperatures to below 50 millikelvin. So the maximum current I was able to achieve with my setup was almost 4 amps. And that was sufficient to make these measurements, but not so large that it could destroy the superconductivity of the sample wire. So now we have all of the nuclear magnetic moments, not all of them, but you have a nuclear magnetization in part of the sample wire, and therefore you have an electrization field. And you're interested in measuring the rate of change of the current I subscript S. And we already know that that rate of change must be nearly infinitesimal because we know that the nuclear electric dipole moment is nearly infinitesimal, and the rate of change is proportional to that EDM, to that electric dipole moment. So we need an extremely sensitive device, a sensor that is extremely sensitive to tiny changes in magnetic flux. The sample wire, of course, as the current changes, generates a changing magnetic flux that in my experiment was detected by a SQUID. SQUID stands for Superconducting Quantum Interference Device. And they are amongst, if not the most sensitive devices that react to changes in magnetic flux. So this SQUID is drawn in this fashion so that we can see some of the pads of the SQUID and leads that go from the SQUID to the exterior of the ADR to the SQUID electronics. In the actual experiment, the sample wire was actually placed against the back of the squid. So all of my data effectively was squid data, and the squid data is a voltage. So what about all of these hyphenated rectangles? Well, these hyphenated rectangles represent magnetic shielding. Surrounding the squid and part of the sample wire is lead shielding. So this is the smallest rectangle around the squid and part of the sample wire. Around that shield is a mu metal magnetic shield. And that large rectangle here is an overall sample assembly magnetic shield that is made of lead and aluminum adhesive. I should mention that at sub-Kelvin temperature, lead is an excellent magnetic shield because it becomes superconducting below 7.2 Kelvin and therefore expels all magnetic fields. Now let's look at some pictures of my experimental components. Here is a picture of the sample solenoid, and it has 358 loops. And this is a picture of the booster solenoid as I was building it. It has two layers. The first layer has 81 loops wound around an aluminum cylinder that has a length of 5 centimeters and a diameter of 10 millimeters. I used yellow tape to keep the loops in place. The second layer had 80 loops. This is a picture of the main solenoid. The superconducting wire is wound around the copper tubing, and the winding is held in place with mylar tape. Here's a picture of the lead shielding that protects the entire sample assembly from magnetic fields and the aluminum adhesive. It is affixed to the 50 millikelvin rod of the ADR. So that rod actually goes to temperatures below 50 millikelvin. Inside that sample assembly shield is the mu metal shield depicted here. Inside that is the lead shielding, and finally the back of the squid, as well as a part of the tantalum wire. And now let's talk about the experimental data. So data was collected for tantalum at all of these temperatures, 52.5 millikelvin, 65, 75, 85, 105 millikelvin. The main solenoid currents that were applied from the external current source were 0 amps, 265 milliamps, and 530 milliamps. At 65 millikelvin, we also collected data for a reverse current that would produce a reverse magnetic field. And the applied current in that case was negative 510 milliamps. We also collected data at non-fixed temperatures where the temperature of the sample assembly was allowed to rise over days up to a temperature below 160 millikelvin. We actually collected data at non-fixed temperatures at 0 amps, 265, and 530 milliamps. But in terms of making further determinations of a measurement of the nuclear electric dipole moment of tantalum, only the 265 and 530 milliamps data was used. So let's look at a small portion of the over 1,000 hours of total of data that I collected in tantalum. Specifically, the y-axis is the squid data, and the x-axis is time. And the squid data is effectively linearly proportional to the current data. And so we're interested in the rate of change of the current data. So we're really interested in the slopes at these various applied currents. In my paper and here, the applied current is a stand-in for the solenoid current, which we know is important in terms of making a determination of whether or not the rate of change of the current follows Curry's law. But the solenoid current is in fact proportional to the main current because it was ultimately induced from the main current. And so we use the main current as a way to label all of the data because it's a lot simpler. So the zero amp data, in other words, there's no induced current, is particularly encouraging. All of the data was encouraging when I first saw it. So the zero amp data is really a measurement of external systematics that could be due to stray magnetic field because there's no induced current, there's no polarization of the bulk material in the sample wire. So there's a slight upward trend, but it's quite small. It corresponds to a change over almost 15 hours of approximately 0.002 volts. The calibration for my squid was that a fluxant, in other words, a quantum of magnetic flux through the Josephson junction that makes up the squid, was calibrated to be 0.741 volts. So this is really a tiny fraction of a fluxant. So that implied that my magnetic shielding for the fixed temperature data was really excellent. And generally speaking, we see an increase in the magnitude of the slope as you increase the solenoid current or the main current. That data was taken at a temperature of 52 millikelvin. Also on the right is the data for the reverse magnetic field taken at 65 millikelvin. And for comparison, I also plot the data at 0.53 amps. And again, very encouraging because that's exactly what we would expect if the current, the rate of change of the current actually follows Curry's law in terms of being proportional to the applied current. And so we have a reversal of the slope when we change the direction of the magnetic field, of the external magnetic field. So overall, using the data at all of the temperatures, I was able to determine that the electromotive force or the rate of change of the current in the sample wire was proportional to the solenoid current or the applied current. So that was obviously an important first result. And I was unable to make the same determination for lead. And that's also important because we already know that the electromotive force is highly suppressed in lead. So this was one confirmation in terms of checking to see if the rate of change of the sample wire current follows Curry's law. The next one, of course, is to verify the proportionality to the inverse temperature. To do this, it's clear that there's a little bit of systematic because of that general upward trend of the zero amp data. And therefore, to get rid of any common systematics, to determine the inverse proportionality with temperature, I subtracted the data collected at 265 milliamps from the data collected at 530 milliamps at each fixed temperature. The idea being to minimize common systematics to all of the tantalum data. This is what was done here. On the y-axis, we have the slopes from the difference data that represent the rate of change of the sample wire current. And on the x-axis, we have the inverse temperature. The black dots correspond to difference data that was taken at the same temperature, but at an applied current of 530 milliamps and 265 milliamps. This point here was data collected at 52.5 millikelvin. This one at a temperature of 65 millikelvin, 75, 85, and 105. But once we had shown that the rate of change of the sample wire current is proportional to the applied current or to the solenoid current, Then we could use data that whose where the difference between the applied current isn't 265 milliamps, and then just factor out the difference. So for example, this red triangle is the slope that was obtained from difference data of the reverse field data set. So, and the difference was between 530 milliamp and 500 and negative 510 milliamp. And this blue triangle actually comes from the difference data between 530 milliamps and the 0 amp data. And only at 52.5 millikelvin did we have a complete data set at 0 amps. So from thousands of data points, we obtain these 7 slopes. And we can perform a linear regression to see how well this correlates with the inverse temperature. And this is what this straight line represents. And it looks very good. And in fact, the p-value that this alignment is purely due to chance. So the probability that this is due to chance is 0.0001. And so such a small probability that this is due to chance is entirely consistent with the fact that the rate of change of the sample wire current is in fact proportional to the inverse temperature. So for the tantalum data, we have shown that the rate of change of the current is proportional to the applied current, and inversely, or the solenoid current, or the magnetic field, the solenoid magnetic field applied on the sample current, and inversely proportional to the temperature. The tantalum data follows the tantalum data for the rate of change of the sample wire current follows Curry's law. And we weren't able to make this determination for lead. But I needed more of a confirmation that this was in fact Curry's law and consistent with the theory of the electrization field. So the data that was collected with the temperature allowed to change was also analyzed. And again, now on the y-axis, we have the squid data in units of volts, and on the x-axis, we have time in hours. And as time increases, generally the temperature increases as well. The blue curve is actually almost 2,000 data points of tantalum, where the temperature is allowed to increase. And the gray curve actually corresponds to lead data. And they're superimposed here because a linear regression was performed of the tantalum on the lead. So why exactly one could perform a linear regression? Well, that's because all things being equal between the tantalum and the lead, they should be strongly correlated, because both data sets were collected in nearly identical experimental conditions, namely the same laboratory, the same equipment, namely the adiabatic demagnetization refrigeration system, and the same solenoids. The main difference between the two sample assemblies is that there was a possibility that the mutual inductance between the lead wire and the squid might be different to the mutual inductance between the tantalum sample wire and the squid. And so the linear regression was performed on the tantalum of tantalum on the lead wire, and that linear regression produced an R squared of 0.993, which is consistent with closely related experimental conditions for the collection of these data sets, even though they were collected at different points in time. This R squared means that only a small fraction represents unexplained variance. 0.007 to be precise is unexplained variance. Everything else is explained by, in principle, by the linear regression. But having collected this data at fixed temperature and having shown that tantalum follows Curry's law, while the control element lead doesn't, makes the following prediction that possibly a lot of the unexplained variance is in fact due to a potentially real electrization field in tantalum that doesn't exist in lead. And I remind you that lead is a control element because nearly none of the naturally occurring lead has a magnetic moment, or should I say about only a quarter of it. So the electrization field is very suppressed in lead. And to test that prediction, the influence of the electrization field of the electromotive force was removed from the tantalum data. And that was actually a straightforward process. So as time increases, the electromotive force will have a cumulative effect. And so a time integral had to be performed on using as an integrand this slope here, which was experimentally determined and could not be changed, divided by the temperature at which each of these nearly 2,000 data points were collected in the tantalum data. And so with this procedure, the experimentally determined electromotive force in tantalum could be removed from the tantalum data. And the result of this process was this red curve. And once again, a linear regression was performed on the new tantalum data where the electrization field or the electromotive force influence, or cumulative influence, was removed on the lead data. And it's immediately visually clear that you have a strong and decisive, actually, improvement in the correlation. This is confirmed with dr squared, which now is 0.998. So only 0.002 of a fraction, so this fraction of unexplained variance still exists. So most of the unexplained variance that we had seen in the unmodified linear regression using the unmodified tantalum data set has actually been explained by the electromotive force. What was done effectively in terms of removing the cumulative influence of the electromotive force was to turn tantalum into lead. And the probability that this improvement is due to chance compared to this case here is in fact zero. Why zero? Because it involves almost 2,000 points. So that probability is so small that it can't be calculated. So looking at the totality of our data, namely the fact that at fixed temperature, tantalum was seen to follow Curry's law as predicted by the electromotive force, but the control element lead was shown not to, and that we could improve the correlation between tantalum and lead when temperature was not fixed simply by removing the experimentally determined cumulative contribution from the electromotive force. And the probability of that improvement is zero. It was shown that there was no other hypothesis that could explain the totality of the data. So other hypotheses that could lead to a variation, a rate of change of the sample wire current includes a systematics coming from external fields or possibly, for example, a residual resistance in the various welding in the superconducting sample assembly. None of those could actually explain all of the data. The only theory that explains all of the data is, in fact, the one that was presented at the beginning of this talk and in my paper, namely the existence of an electrization field. And so using this experimentally determined slope, value for the magnitude of the nuclear electric dipole moment of tantalum could be extracted, it is that value, 3.39 by 10 to the negative 32 E centimeters. E is just the electron charge, and it was shown that this magnitude is greater than 0 at a 99.99% confidence level. And so that result immediately has certain implications in terms of the motivations we discussed about why it's important to measure nuclear electric dipole moments. Namely, if we assume that the neutron electric dipole moment is of the same order of magnitude as a typical nuclear electric dipole moment, then that would mean that the neutron electric dipole moment is of the order of 10 to the negative 32 E centimeters. The issue here is that that value, that order of magnitude, falls in the range of what physicists believe is predicted for the neutron electric dipole moment in the standard model of particle physics alone. And so if this is confirmed, and if this is experimentally confirmed, then that would eliminate a number of theories that go beyond the standard model. But we're not close yet to making this determination. But the method presented in this talk and in the paper shows a clear path to getting to the neutron electric dipole moment. Because this method can be used to measure the nuclear electric dipole moment of dozens of atoms, and not just atoms from elements that are superconducting on their own, like lead or tantalum, but also elements that are not superconducting on their own, but are in fact superconducting within compounds. And so if we can create a large data set of nuclear electric dipole moment, that would allow us to over-constrain the parameters that scientists believe are the biggest contributors to a nuclear electric dipole moment. So these parameters, that include, among others, the neutron electric dipole moment, as well as the proton electric dipole moments, and other parameters that violate time invariance, they could all be determined by a sufficiently large nuclear electric dipole data set, if we have enough of them. And the way this would work is that these parameters could be determined and then used to, for example, determined by a subset of this data set of nuclear electric dipole moment, and then used to see if these parameters can then predict the value of the nuclear electric dipole moments from in all of the other nuclei that were not used to determine these parameters. And in fact, this has already been done, this method, with the same theoretical concepts, has been done for nuclear magnetic moments. There's a large set of nuclear magnetic moments that have long been known, and scientists have long determined the most important parameters that contribute to nuclear magnetic moments. And two of these parameters are the neutron magnetic moment and the proton magnetic moment. And using these parameters, scientists have been very successful at predicting the nuclear magnetic dipole moment. So effectively, the exact same procedure could be performed for nuclear electric dipole moments that would allow us to determine all of these parameters, including the neutron electric dipole moment. Another important application of this method is that it can also be used to determine the electron electric dipole moment using P-wave superconductors. And if you want to see more detail, please take a look at my paper that's available on loisat.org. The last application I wanted to discuss is the detection of the cosmic dark matter axion wind. What is the cosmic dark matter axion wind? Well, the visible part of the galaxy of the Milky Way is inside a dark matter halo that is effectively static. That means that the halo doesn't revolve about the galactic center the way stars do. That implies that as the solar system progresses along its orbit about the galactic center, it moves through the dark matter halo. From the perspective of a laboratory on Earth, there's a cosmic dark matter wind. If the dark matter halo contains axions or axion-like particles, there would be a cosmic dark matter axion wind. The important property here is that the cosmic axion wind can induce an oscillating nuclear electric dipole moment that could be detectable using the method I used to measure the nuclear EDM of tantalum. What we would look for now is an oscillating supercurrent in the superconducting wire. The frequency of the oscillating current would be proportional to the axion mass, and the density or the amplitude of the oscillating current would be proportional to the local density of the dark matter at the position of the laboratory. That means that the amplitude could vary, fluctuate, because the Earth rotates about its axis and orbits the Sun, and because of phenomena like dense dark matter hairs. I really started this experiment about 9 years ago when a grant I applied for at the Jet Propulsion Laboratory where I worked to perform this experiment was rejected because the reviewer believed it was unphysical. A paper sketching out the basic idea was rejected for publication because one of 3 reviewers rejected it. I was laid off from JPL for lack of funding. I carefully considered the objections of the reviewers and answered all of them. At that point, I felt I had an obligation to perform the experiment and proof of concept with the resources available to me. We sold our house, and a portion of the proceeds went towards funding the experiment. I also did a lot of tutoring, private tutoring, something I thoroughly enjoyed, to make ends meet. Over the last 5 years, working alone with a lot of trial and error, I designed the experimental concept, implemented it, collected the data, analyzed it, and wrote the final paper. Going forward, I'd like to build a team of scientists at LOISAT to design a sample assembly that is more compact and can be manufactured with different elements with the ultimate goal of detecting the cosmic dark matter axion wind. So I ask you to please donate to the LOISAT Detecting the Dark Matter Axion Wind fundraising campaign so that LOISAT can continue writing in the pages of scientific discovery. I also ask you to consider donating to the LOISAT Shields and Spear fundraising campaign because one thing I rarely encountered in my career during my career as a scientist was other Black scientists. There are institutional forces in society that systematically produce the same weak math skills and miseducation generation after generation in the United States and abroad. I founded LOISAT because there are undoubtedly potentially brilliant Black scientists that will never have the option to actually contribute to scientific discoveries. I founded LOISAT because scientific knowledge belongs to everybody, regardless of background. I founded LOISAT because weakening these systemic institutional forces that produce these racially differentiate results in STEM fields will make for a better world and will benefit everybody. Thank you for listening and thank you for donating.